Hello everyone, and welcome to today's video lecture, which is on the complex sine and complex cosine functions. That is to say, this video lecture is about taking the sine or cosine of a complex number as opposed to a purely real number. So in today's video, we're going to do a few things that are pretty straightforward. I'm going to show you how to take the sine or the cosine of a complex number. So we're going to look at the definition for that, and then I'm going to show you how it's derived. So specifically, we're going to prove the following. We're going to prove that cosine of z, where z is a complex number, is equivalent to taking e to the iz plus e to the negative iz over 2. We're also going to prove that the sine of z, where z is a complex number, that's equal to e to the I times z minus e to the negative I times z all over 2 times I. So first I'm going to ask you to recall Euler's identity, which states that e to the ix equals cosine of x plus I times the sine of x. Okay, I have a video where I derive this identity. It's extremely important. This is Euler's identity. And now what I'm going to ask you to do is to consider what would happen if we were to change our value x to negative x. Well, let's just apply the formula and see what happens. So we'll have e to the I times negative x. That will equal cosine of negative x plus I times the sine of negative x. But cosine of negative x just equals cosine of x. And the reason for this is that the cosine function is what's called an even function. It has this property of being symmetrical across the y-axis. So cosine of negative x equals cosine x. Meanwhile, sine of negative x equals negative sine of x. And this is because sine of negative x is what's known as an odd function. It has symmetry through the origin. So we can rewrite this in the following way. We would write e to the I times negative x. And can I just simplify that here to e to the negative I times x? Okay, that would equal cosine of negative x, which just equals cosine x. And I sine of negative x would be minus I sine x. So we can group these two facts together here. We have e to the ix equals cosine of x plus I times the sine of x. And e to the negative ix equals cosine of x minus I sine of x. And so now, if I add these two equations together, I would have e to the ix plus e to the negative ix equals cosine of x plus cosine of x is 2 cosine of x, and the plus I sine x and minus I sine x cancel. So we're about to derive this identity for cosine of x because all I have to do now is divide both sides of the equation by 2. When I do that, I get e to the ix plus e to the negative ix all over 2 equals cosine of x. So we can put a box around this formula. This is a formula that's worth committing to memory. And to derive the related formula for the sine function, instead of adding these two equations, we actually subtract them. So let's do that here now. We'll have e to the ix minus e to the negative ix equals, well, the cosine terms will just cancel there. And I'll have I sine x minus I sine x. So I have a double negative sign there, so that double negative just becomes a plus sign. Let me change that. So now we have e to the ix minus e to the negative ix equals 2I sine x. And if I divide both sides of the equation by 2I, I get the formula e to the ix minus e to the negative ix all over 2I equals sine x. That's the other formula worth committing to memory. So Let's put a box around this one also, so we have our formulas for cosine of x and sine x in terms of Euler's identity. So now we want to ask whether these same identities would be valid if we replaced our real variable x with a complex variable z. So we're going to essentially define sine and cosine now for complex numbers based on these same identities that we've derived. So our goal in the remainder of this video is to prove that cosine of z equals e to the I times z plus e to the negative I times z over 2, and that sine of z equals e to the I times z minus e to the negative I times z over 2i, for z a complex number as opposed to just a real number. So to prove this, I'm going to ask you to recall some of your trigonometry knowledge from high school trig class. Specifically, we're going to make use of the following identities: that cosine of a plus b equals the cosine of a times the cosine of b minus the sine of a times the sine of b. And we're also going to use that sine of a plus b equals sine of a times cosine of b plus cosine of a times the sine of b. So I'll move those identities to the top of the screen, and I must admit that when I was a high school student I was somewhat mystified as to how they were derived, but it's very easy to prove these identities using Euler's formula, so let's do that now. So we have e to the I times a plus b equals cosine of a plus b plus I times the sine of a plus b. So first I'm going to rewrite e to the I times open parenthesis a plus b, close parenthesis, as e to the I times a plus I times b. And then by the laws of exponentiation, that would equal e to the I times a times e to the I times b. So this would then equal cosine of a plus I sine of a, that's e to the I times a right there. I'll put some bigger parentheses around that expression, times cosine of b plus I times the sine of b. Parentheses again around that one. So let me just replace that there. So we have e to the I times a plus b equals cosine of a, I'm going to multiply this out now, times cosine of b plus cosine of a times I sine of b, okay, plus I times the sine of a times cosine of b, and then finally plus I times sine of a times I times the sine of b. So we can clean this expression up a little bit now. We'd have e to the I times open parenthesis a plus b close parenthesis equals cosine a times cosine b, and then in that expression at the end there, that last term I sine a times I sine b, the I times I becomes a -1, so we have minus sine a times sine b. Okay, those are the real terms. And then for the imaginary terms, those are the terms that still have an I left over in them. This would equal I cosine a times sine b plus, here's the other imaginary term, I times sine a cosine b. And now I'm just going to factor out the I from those two terms, so it's outside the parentheses there. So now I'll just move that expression up to the top line there, and we have two equivalent ways of writing e to the I times a plus b. So now we can equate the real terms and the imaginary terms in these two expressions. So there's cosine a plus b, which must equal cosine a cosine b minus sine a sine b. Meanwhile, sine a plus b, that has to equal cosine a sine b plus sine a cosine b. So just cleaning up the board a little bit here, we have that cosine a plus b equals cosine a cosine b minus sine a sine b. We've proved that identity. and that sine A plus B equals sine A cosine B plus cosine A sine B. So with those sum of angle formulas firmly established, we can now prove our formulas for sine and cosine with our input z as an imaginary number. And we'll do that by letting z equal a plus b times I. If we do that, then we would have cosine of z equals cosine of a plus bi, which we know by our sum of angles formula above would equal cosine of a times cosine of b times I minus sine of a times sine of b times I. So let me put that all on one line, and now we can make use of our definition of sine and cosine in terms of Euler's identity for the real variable case to extend this definition to complex variables, because we'll have cosine of a equals e to the I times a plus e to the negative I times a over 2. This is times cosine of bi, which would equal e to the I times bi plus e to the negative I times bi over 2. And I'm subtracting from this sine of a times sine of bi, so sine of a would be e to the I times a, let me put a bracket around this, minus e to the negative I times a, all over 2i, times, okay, sine of bi is e to the I bi minus e to the negative I bi, all over 2i, close the bracket. All right, so let's put that all on one line here, and I'll just put brackets around the cosine terms there. And now we can clean up this expression a little bit. So in my cosine bi term, that equals e to the ibi plus e to the negative ibi over 2. Well, e to the ibi is the same thing as e to the I squared b. I squared is just negative 1, so I'm going to rewrite that as e to the negative b. Similarly, e to the negative I bi, so negative I times I is just positive 1, so that just becomes e to the b. Similarly, in the sine bi term, in that second bracketed expression, e to the ibi there, that would become again e to the negative b, and e to the negative ibi, that would just become e to the b. So now when we actually multiply these terms within the brackets, we get the following. We get that this expression equals e to the I times a times e to the negative b. So I'm just going to write this more simply as e to the ia minus b, using the laws of exponentiation, plus e to the I times a plus b. Okay, plus e to the negative I times a times e to the negative b, so just e to the negative I times a minus b, plus e to the negative I times a plus b. So that multiplied the terms in the numerator, and then the denominator is just 4. Okay, so I'll close the brackets there. And this is going to be minus, open bracket, e to the I times a times e to the negative b, so minus b, minus e to the I times a plus b. Now let's do the last two terms. This would be minus e to the negative ia times e to the negative b, so it will be minus e to the negative ia minus b. And for the last term in this expression, I have two negative quantities being multiplied together, negative e to the negative ia times negative e to the b, so this will be plus e to the negative ia plus b. And in the denominator, I have 2i times 2i, so that will become negative 4. So our first simplification is to notice that we have a minus sign in front of that second bracketed quantity there and a minus 4 in the denominator, so those negative signs cancel and that minus becomes a plus sign. So now we have a common denominator of positive 4, and when we actually combine these two fractions, we can cancel some terms. So e to the ia plus b is canceled by minus e to the ia plus b in the second fraction, and e to the minus ia minus b is canceled by minus e to the minus ia minus b in the second fraction as well. So let me just shift that second term over to make room here. So when we combine everything, we get that cosine of z equals 2 times e to the ia minus b plus 2 times e to the negative ia plus b, all over positive 4. And when we divide through by 4, the 2's cancel in the numerator, and that 4 in the denominator becomes a 2. And so we finally get that cosine of z equals e to the ia minus b plus e to the minus ia plus b all over 2. But now we want this expression to be in terms of z. And so to do that, I'm going to factor out I from the exponents. So when I do that, I have e to the I times, open parenthesis, a minus b over I, okay, because I factored out the I from both terms there, so close parenthesis here, plus, and I'll actually factor out a negative I in the second term, e to the negative I times, open parenthesis, a plus b over negative I, close parenthesis, all over 2. And you'll see why I've done that in just a moment. But first I'll ask you to recall the following fact, which is that 1 over I equals negative I, and by the same token, 1 over negative I equals positive I. So when we make use of that fact, we have e to the I times a minus b over I there. Well, minus b over I is the same thing as minus b times 1 over I or minus b times negative I. Okay, so I'll close parenthesis on that. And this is going to be plus e to the negative I times a plus b over negative I. b over negative I is the same thing as b times I. And this is all over 2. So we now have cosine of z equals e to the I times, open parenthesis, a minus b times negative I, close parenthesis, plus e to the negative I times, open parenthesis, a plus bi, close parenthesis, all over 2. Well, I hope some of you can see where we're going with this. Because now the expression would read cosine of z equals e to the I times, open parenthesis, a minus b times negative I, so a minus bi, and that double negative there, of course, just becomes a positive, so we have e to the I times, open parenthesis, a plus bi, close parenthesis, plus e to the minus I times, open parenthesis, a plus bi, close parenthesis, all over 2. But a plus bi just equals z. So we end up with cosine z equals e to the iz plus e to the negative iz all over 2. And we've proved this identity for the complex case. We've extended the cosine function to all complex numbers. So now let's use the same strategy to derive the formula for the sine of a complex number, z. So here we go. Sine of z would equal sine of a plus bi, close parenthesis. And we have our sum of angles formula for the sine up there. Sine of a plus bi would equal sine of a times cosine of bi plus cosine of a times sine of bi. And using our definition of the sine in terms of Euler's identity, we would have sine of a equals e to the ia minus e to the negative ia all over 2i times cosine bi, well, that would equal e to the ibi plus e to the minus ibi all over 2. And we can put brackets around that product there. And that will be plus, open brackets, cosine of a, well, that's just e to the ia plus e to the minus ia all over 2 times sine of bi, well, that's e to the ibi minus e to the negative ibi all over 2i, close the brackets. And now I'll just move that all to one line. And when we do this multiplication, we get e to the ia times e to the ibi. Well, e to the ibi is just e to the minus b. So this becomes e to the ia minus b. Plus, here's the next term, e to the ia times e to the minus ibi. That just becomes e to the ia plus b. Minus e to the negative ia times e to the ibi, that's e to the negative ia minus b, minus e to the negative ia times e to the minus ibi, that's just e to the negative ia plus b, all over 2i times 2, so all over 4i. And now moving on to the next bracketed term, multiplying this out, we would have e to the ia times e to the ibi, which equals e to the ia minus b. And then e to the ia times negative e to the negative ibi, that would just equal minus e to the ia plus b. And then the third term here would be plus e to the negative ia times e to the ibi, so that would be plus e to the negative ia minus b. And the final term would be plus e to the negative ia times negative e to the minus ibi, so we would get minus e to the negative ia plus b, all over 4i again. So with that common denominator of 4i, we can make some cancellations. E to the ia plus b is canceled by minus e to the ia plus b, and minus e to the negative ia minus b is canceled by positive e to the negative ia minus b. And so we're left with sine of z equals 2 times e to the ia minus b minus 2 times e to the minus ia plus b, all over 4i. So we divide through by 4, the 2's cancel there, and we're left with sine z equals e to the ia minus b minus e to the negative ia plus b, all over 2i. And now to get this expression in terms of z, we factor out I from the first exponent, so we get e to the I times open parenthesis a minus b over I, close parenthesis. And then the second term we factor out negative I, so we get minus e to the negative I times open parenthesis a plus b over negative I, close parenthesis, all over 2i. And then b over negative I just equals b times I. So we can write that this equals e to the I times a plus bi minus e to the negative I times a plus bi, all over 2i. But a plus bi just equals z. So this equals e to the iz minus e to the negative iz over 2i. And we've proved the identity for sine of z. We've extended the sine function to complex numbers as well. So again, we have proved that cosine of z equals e to the I times z plus e to the negative I times z all over 2. And sine of z, again where z is a complex number, guys, equals e to the I times z minus e to the negative I times z all over 2i. So let me put a big box around these very important identities for a complex analysis that, again, extend the meaning of sine and cosine to complex numbers. Well, thank you so much for watching. I hope you enjoyed this video, and if you did, please like or subscribe to my channel. Thanks again.